Hey there folks, I've had a request to go over the exam, so I'm going to do that right here. What you see on screen is the copy of the exam. I also have the background information on the systems that we're going to be looking at. And as I did with the small group activity walkthrough that I did, I have a window up over here that is essentially going to be a scratch pad for me. You don't need to worry about what this program is. It just lets me type in equations and such pretty easily over here rather than writing them down on paper. So let's take a look at what we've got here. The first series of questions are all about converting into molarity the concentrations that we have here. Now there are quite a few of them. So I make the suggestion that it would be convenient to make a spreadsheet to do this. So I'm going to talk through how to do that. So let's put the ion in this column. We'll put the part per thousand by mass concentration here, and we don't yet know what other information we're going to need. So Cl minus, Na plus, SO4 2 minus, Mg2 plus, Ca2 plus, K plus, HCO3 minus, Br minus, BOH4 minus, SR2 plus, F minus. Okay. And just putting in the numbers, 345, 10.752, 2.701, 1.295, 0.416, 390, 0.145, 0.006, 0.027, 0.013, 0.001. Okay. Now we need to figure out how do we actually do this conversion. So we'll put that over here and let's think about it. Parts per thousand by mass. So for the first one, the Cl minus ion, what we are looking at is 19.345 grams of the chloride ion per 1,000 grams of the solution. That's what parts by thousand means. Okay, it's how many parts out of the 1,000. In order to do this conversion, we are trying to get to, so we want this to be in moles of Cl minus to make it molarity divided by liters of solution. That's what we're trying to get to. So we need to go from grams of solution to liters of solution. How do we do that? Well, it's in water. So a gram of the solution is going to be 1 milliliter of the solution. And we need to get to liters, so we want 1,000 milliliters over 1 liter solution. Okay, so grams of solution cancels, milliliters of solution cancels, and we are left with liters of solution in the denominator. Okay. Now we need to get from grams of chloride to moles of chloride. Hopefully you know you use the molar mass to do that. So we need to have grams of the chloride ion down here, and we need to have 1 mole of the chloride ion up here. So we need to know the molar mass of chloride. Well, let's bring up our, of this we might need a periodic table. So go somewhere here. Chloride is 35.45. So we will call this 35.45. Excuse me, I'm putting that in the wrong place. So this now becomes here 35.45 grams of chloride. Okay, now that we see how to do this calculation, because if you notice here, grams cancel, we're at moles, so we're where we need to be. Now that we see how to do this calculation, let's set up the spreadsheet to do all of them for us. The one piece of information we need is the molar mass. So in the spreadsheet, we will put molar mass. Okay, this is 35.45. And so what the calculation we do to get the concentration in molarity is we take the value we have here, divide by 1,000, multiply by 1,000. Those cancel each other out. So basically all we do is we take this and divide by the molar mass. So this is going to be equal to that divided by that. Okay, so I'm going to copy that formula all the way down here. And as soon as we put in the molar masses that we need, have all of the numbers that we need. So coming back to the periodic table, I'm going to move that one to this side now. Sodium, we look at sodium, 22.99. Sulfate, so this is going to be equal to the sulfur, 32.06, plus 4 times the oxygen, which is 15.999. Okay. Magnesium, that is going to be 24.305. Calcium is going to be 40.078. Potassium is going to be 39.098. HCO3, so this one is going to be equal to 1 hydrogen, 1.008, plus 1 carbon, 12.011, and plus 3 oxygens, so 3 times the oxygen, 15.999. Bromine, that is going to be 79.904. Borate, boron with 4 hydroxides on it. So that is going to equal the boron, which is 10.81, plus 4 times the oxygen, which is 15.999, plus 4 times the hydrogen, 1.008. The strontium is 87.62, and the fluoride is 18.998. Now, at this point, we have all of our first sets of answers. So what we can do now is just put those numbers in. And then we have to be careful about this one because it's in this Excel form of scientific notation, which we don't want. So what we need to do is switch it out of scientific notation into a number form. And let's get some extra digits. There we go. Now, what's the total concentration of the ions? Well, that's just going to be the sum of these. So equals the sum of all of these. There we go. All right. If seawater were placed in 1/2 of a U-tube, this is going to be an osmotic pressure calculation. All right. So let's move this over here and let's look at how we do osmotic pressure. So pi equals RT times the concentration in molarity. Well, we just had the concentration in molarity, which is right here. Okay, so we have that number, molar, times our value for R. So let's find gas constant. We're also going to need our temperature. I'm going to go ahead and put the temperature in so that we can see our units pretty as well as possible. So what we have here, remember this is moles per liter. Our temperature is, from the problem, is, let's see, 25 degrees C. So that is going to be 273.15 plus 25 to become 298.15 Kelvin. And we need our gas constant, and we would like it in units where moles, liters, and Kelvin cancel, and it's asking for the answer in atmospheres. So we want liters atmospheres per mole Kelvin would be ideal. Liters atmospheres per mole Kelvin. So that's this one. So our value for R is going to be 0.082057366080960. Right? We certainly don't need that many, but liters atmospheres per mole Kelvin. And if we look through here, we see liters cancel, moles cancel, Kelvin cancels, we're left in atmospheres. Now, this program I have here acts like a calculator. So I'm going to take that number, and take this number, multiply them together, and we get 27.4. So now how many significant digits should we put in? Probably not all that many, but you know what? It doesn't hurt to put in a bunch of extras. All right. Now, if a meter-deep column of seawater exerts a pressure at its base of 0.0123 atmospheres, what depth of seawater would be necessary to counteract the osmotic pressure? So what are our units here? That is how many atmospheres we have. So let's take it to there, any atmospheres. And we now have a conversion factor, don't we? Because for every 0.123 atmospheres, that is going to be 1 meter of seawater. Okay, so 27.3739 divided by 0.123, again using this as a calculator, we have 222.5. So, and that's in meters. There we go. Now, we now want to create 100 milliliters of a solution with the same fluoride ion concentration as seawater. All right. What was our concentration of fluoride? Let us take a look. It was this concentration in molarity. So we want 0.1234526 moles of fluoride per liter of solution. That's the number that we are trying to get. And we only can do it using a 100 milliliter solution with volumetric flasks. And we are adding to it, and we are doing this by using sodium fluoride as the source of the fluoride ions. So that means that we want 100 milliliters of the solution. So we're going to take this and multiply it by 100 milliliters. I'm going to put it over 1 so that you can see what's canceling and what's not. So the milliliters we need to cancel with the liters. Remember, multiply a concentration by a volume to find the number of moles. Okay, so but we need to have the liters cancel. So 1,000 milliliters is 1 liter. So milliliters cancel, liters cancel, and we now have moles of fluoride. But we don't want fluoride here. Every mole of the fluoride corresponds to 1 mole of the sodium fluoride, because when this dissolves, you get 1 mole of the fluoride ion. And now we can convert that to grams to find out how much we need to weigh out. 1 mole of NaF. And we now need to go back to our periodic table, and sodium is 22.99 for the sodium. Fluoride is 18.998. So again, using this as a calculator, we have 41.988 grams sodium fluoride. All right. So now we can calculate what mass we need. 0.1234526 times 100 divided by 1,000 times 41.988. And the result is going to be grams of sodium fluoride. So we have that many grams of sodium fluoride that we need. The problem is that we only can weigh to the nearest 0.1 gram. Now, if you look at the volumetric flask and the volumetric pipette, if we take 1 milliliter out of the flask, whatever concentration we have, put it in a new flask, and then dilute to 100 mils, then we change the concentration by a factor of 100. So what that means is that if we start with 2.2 grams, then after the first dilution, it'll be down to 0.02 grams, 22 grams. And after the second dilution, it'll be down to 0.00022 grams, which is what we want. So what we need to do is weigh out 2.2 grams and do 2 dilutions by a factor of 100. So we weigh 2.2 grams. We transfer it to a new volumetric flask. We add water below the mark, stir until dissolved, fill with water to the mark so that we now have this first concentration that we need. We stir to mix. We extract a milliliter of the solution from the previous step, transfer it to a new flask, fill with water to the mark. We don't have to go through a dissolution step because it's already dissolved this time. Fill with water to the mark, stir to mix. Extract 1 ml of the solution from the previous step for our second serial dilution. Transfer it to a new flask. Fill with water to the mark. Stir to mix. Declare victory. We're done. Whoops. There we go. Now, strontium borate does not have a known solubility level. Based on the data given, what would you estimate its solubility to be? Give your answer as in the chart in grams per 100 mils of water to one significant digit. Okay, so we need to go back to this. We're looking for strontium borate. So strontium borate is not available, but we have how much strontium is dissolved and we have how much borate is dissolved. The molarity, because we need to make sure that we are looking at the amounts correctly, because strontium is +2, borate is -1, so our compound is going to be SR B OH 4 2. Okay, so that means we need twice as much borate as we do strontium. So let us see if we divide that by 2, we have 0.171 molar of double that. This is the smaller of the two. So that means that we have a concentration of this amount of strontium borate in solution. So 0.0001484 moles of SR. I'm going to copy this. That 2 should have been a subscript. All right. We have moles of this in 1 liter of solution. We want this in units of grams per 100 mils of water. Easiest way to do this, let's figure out how many grams are in a liter, and then we'll divide it by 10 to have 100 milliliters. So we need the molar mass of strontium borate. So 1 mole, apparently I hit caps lock, 1 mole of this I didn't get the strontium apparently. All right. And this, we need to know how many grams that is. Well, conveniently, over in here, we have the molar masses of these ions already. So what we need for the molar mass is to take this molar mass times 2 plus this molar mass. So this is going to be 245.296 grams. And that tells us how many grams we have in 1 liter of solution. So if we take that times that, and then divide that by 10, that tells us how many grams are in 100 milliliters of solution. And so our answer is this number right here, 0.00364019. All right. 17. Is your answer to the previous question an upper bound or a lower bound? Well, we know this much can dissolve in water, but we don't know that more couldn't dissolve in water. So this is going to be a lower bound. At least this much can fit in. All right. If you treat the concentration of sodium chloride like a limiting reagent problem, what is the concentration of NaCl in seawater in molarity? So the idea here is we make sodium chloride from these two. If it's a limiting reagent problem, then that means whichever one is smaller is the one you want. So that's the molarity, but it's saying to do it to one significant digit, so that's going to be 0.5. 0.5. How much more sodium chloride would have to be added to seawater for the solution to be saturated? Give your answer in grams per 100 milliliters. All right, so if we're starting at 0.5, you can do it a couple different ways. One would be to figure out the saturation concentration in molarity, subtract this from it, and then convert that to the right units. The easier way to do it is to go ahead and convert 0.5 molar NaCl into grams per 100 mils units, because here we already have the concentration in grams per 100 mils that's saturation, and then we should be able to just subtract the two. So 0.5 molar sodium chloride is the same as 0.5 moles in 1 liter of solution. We need to convert from moles to grams. So 1 mole NaCl is going to be a certain number of grams NaCl, and we can again get that from our spreadsheet over here. So our molar mass of sodium chloride is going to be that one plus that one. So this is 58.44. When you we have a concentration, we multiply it by the amount of solution we have, which for this set of units is 100 mils. So times 100 times 100 mils, or to make the liters cancel, 0.1 liters. That tells us how much we actually have in seawater. So that times 0.5 times 0.1 tells us that we have 2.922 grams of sodium chloride in salt water. Saturation is 36. So 36.0 minus 2.9 tells us that we would need to add an extra 33.1 grams to our 100 milliliters. The point of this question is that as salty as seawater tastes, we're a long way from saturation. Really long way from saturation. Okay. If you wanted to precipitate the magnesium ions from seawater into some ionic solid, but not the calcium ions, what counter ion already present in seawater would you add more of? Select all the choices that should work. So we want to precipitate magnesium, but we don't want to precipitate calcium. So what we want is something where is some counter ion where the magnesium solubility is really low, but the calcium solubility is really high. So that looks like bicarbonate, because this one is low, this one's high, and the borate. This one is low, this one's high, comparatively. So if you add bicarbonate to it, this is going to precipitate, and this won't. So bicarbonate, borate. Borate, bicarbonate. Moving on. What intermolecular forces are present between water molecules in the pure liquid? Select all that apply. So I gave you a PowerPoint that shows you a simple way to go through that information. Hopefully you know that water is not an ion, but it is a dipole. So you have these, and we know it has hydrogen bonding. What intermolecular forces are present within a solid crystal of sodium chloride? Well, sodium chloride are ions, so you have ion-ion interactions. It is not a dipole because it's just a positive ion and a negative ion, and there are no bonds, so you can't have dipoles. So you skip that. You can have an induced dipole because there are electrons that can be polarized by the ions. No dipoles. We do have London dispersion interactions. There's no hydrogen, so you can't have hydrogen bonding. All right. Between sodium chloride and water. So sodium chlorides are ions. Water is a dipole. So you have ion-dipole interactions. Water is not an ion, so between the two you don't have ion-ion. You certainly have the ion inducing a dipole in the water. Sodium chloride, those are not dipoles, so you can't have dipole-dipole. Dipole-induced dipole, the water's a dipole, and it can induce a dipole into the sodium chloride, so yes. London dispersion, always. Hydrogen bonding, well, sodium chloride is neither a donor nor an acceptor, so between the two, there is no hydrogen bonding. Okay. Which salt has a higher molar solubility in water? Sodium chloride, sodium bromide. Well, we can get more bromide in by mass, but we need to know by molarity. So we need to take 36.0 grams of sodium chloride in 100 milliliters of solution. Remember, that's what we have here. We now are trying to get this in molarity, so we need to have 1 liter solution. Okay, so our denominator is good now. We now need to use the same sodium chloride conversion factor we had up here. And that will give us, except it's upside down, isn't it? So let me swap those. There. So that now the grams cancel, and we're left with moles per liter. So 36 times 1,000 going across the numerator. In the denominator, 158.44. Can't type. Plug that into your calculator in this case, and we get 6.1. Now we want to do exactly the same thing for the sodium bromide case. The solubility from the table is 90.8. That's the same. Our molar mass is different. So we're going to come over here. We're going to do the sodium bromide is going to be equal to the the molar mass plus the bromide ion molar mass, 102.894. So we have 90.8 times 1,000 in the numerator. In the denominator, 100, 102.894, and plug it into your calculator, and we have this concentration. So the molar solubility, just to be very clear, it's bromide here. I didn't update that when I did the cut and paste. So the sodium bromide is more soluble in water, has a higher molar solubility. Sodium bromide. Okay. Select all the reasons that both would result in this solubility trend. Sodium bromide is more soluble than sodium chloride, and makes chemical sense with what we know about sodium chloride versus sodium bromide. So let's worry about the chemical sense part first. Dipole-induced dipole forces between water and bromide are stronger than those same forces between water and chlorine. Well, the water is the same in the two cases. It's only bromide versus chloride. Which of the two has more electrons? Bromide. So bromide is going to end up having a larger induced dipole than chloride will. And so the dipole-induced dipole forces between water and bromide are indeed stronger than those between water and chloride. Okay, I'm not. So that means this one, which is going the opposite direction, is wrong. The ion-ion forces within sodium bromide are stronger than those within sodium chloride, or vice versa. Well, let's think about that. The charges are the same, but bromide is larger than chloride, which means that the charge is more spread out on the bromide ion than it is on the chloride ion, and so the chloride is going to have stronger intermolecular attractions. So the ion-ion forces with sodium bromide are weaker than those within sodium chloride. Ion-induced dipole forces within sodium bromide. Again, it's the same argument. Bromide and chloride are the things that are different. Bromide has more electrons, so the ion-induced dipole effect is going to be stronger in the sodium bromide case. There are no such things as sodium bromide molecules. There are no such things as sodium chloride molecules, so neither of these can be correct. Hydrogen bonding to bromide ions. There is no hydrogen bonding to either bromide or chloride ions, so neither of those are possible. Ion dipole forces between bromide and water compared to chloride and water. The ion for bromide has the charge more spread out over a larger volume because bromide's larger than chloride. So, but that way the water and the chloride can get closer together, and as a result you end up having a stronger ion dipole force for chloride and water. So we have now listed all of the ones that make chemical sense given this. Now we need to figure out which of these show the same solubility trend that we just identified, where sodium bromide is more soluble in water than sodium chloride. So this one here, this is talking about the forces between water and the ions. And so we want these forces to be strong in order to favor solubility. And the water bromide ones are stronger than water chloride ones, so this goes in the same direction. Ion-ion forces within sodium bromide and sodium chloride. In this case, we are looking at wanting to have weaker forces for the sodium bromide because we are breaking these forces in order to form the solution. So this one also goes in the same direction as the trend that we were looking for. Ion-induced dipole forces within sodium bromide are stronger than within sodium chloride. Now this means that in the salt, in the solid, the sodium bromide has stronger of this, and we're trying to break those. So this one is going the opposite direction. So we get rid of that. Last one we have to look at is here. Ion dipole forces between the ion and water. We want strong forces in this case for the bromide, and here we are saying that they are weaker. So this one goes opposite of what we want. We now have those two. Okay. We now begin the System 2 set of questions. This question is very similar to examples that I did in class using the body-centered cubic structure. Here, we are doing the face-centered cubic structure. So let's think about the face-centered cubic structure. We know that anions are touching across the face diagonal. So the face diagonal equals 4 anionic radii. Okay? Now, the face diagonal is also a right triangle where the two edges, the two sides, are the unit cell length. So the edge unit cell length squared plus another one squared, the Pythagorean theorem, equals the face diagonal squared. Okay, so this is 2e squared equals our face diagonal squared, which is going to be 16 RA squared. Let's divide through. So then E squared is going to equal 8 RA squared. And so E equals square root of 8, which is 2 times the square root of 2 RA. The background information we had also tells us that the cations are in the octahedral interstices, and the octahedral interstices can be found at the center of the cell and in the middle of each edge of the unit cell. That means that the edge of the unit cell corresponds to an anion radius, 2 cation radiuses, and another anion radius as we go across. Okay, so let's simplify that here. So we now have that equals this. Okay, so take that, let's subtract this from both sides. That. Our cation, let's divide through by 2. So we're going to take this. We're going to divide by 2 on both sides. And let's factor out our RA. So and we now have this. And here what I'm doing is something to force this to this program to actually plug in and, for the numbers. So what we find is that the anion radius can only be 41% of the cation radius. That is this value right here, 0.414. And we could add in extra, but 3 decimal places. All right. Based on the information, which following alkaline earth chalcogenates could not adopt this structure? So the information here says that like charges repel one another, and so the cation typically needs to be larger than the size of the interstices to force the anions to be separated by at least some space. So this is the minimum size that we need. So what we need to do now is to take the anion radius, so for oxygen it's that, and we need to multiply by this, and that's going to give us our cutoff. Okay, so there's oxygen, and we do the same thing for each of them. 184 for sulfur, 198 for selenium, and 221 for tellurium. Okay, so these are now the minimum sizes that can work. We need things that are larger than these. Okay, so which ones don't work? Well, let's see. The ones that don't work for the oxide is going to be beryllium. So beryllium oxide doesn't work. Come back over here. For the sulfide, which ones don't work? Magnesium and beryllium, because those are smaller. So magnesium, the sulfide, magnesium and beryllium. For the selenide, which ones don't work? Magnesium and beryllium, because they're too small. So the selenide are magnesium and beryllium. For the telluride, it's 91. The 2 that are smaller are magnesium and beryllium. So the 2 that don't work are magnesium and beryllium. That's it. One example compound that should work is calcium oxide. What should be the unit cell edge in picometers? So this one is really straightforward because remember this right here. We have, even though the unit cell size has been expanded, it is still true that the cation and the anion are touching each other along the edge. So calcium oxide, calcium, the radius is 100, the oxide is 140, and we want 2 of each of those. So it's going to be 2 times that plus 2 times that, 480. Edge length is 480. Oh, can't type. 480. How many calcium ions are in each unit cell? All right, so for this one, it is probably worth doing this and taking a look. So we know we have a calcium ion dead center, and we know we have a calcium ion at each edge. How many edges are there on a cube? There are 12. So there are 12 edges, but each edge is in 4 separate unit cells. So we're going to divide that by 4, so that gives us 3. And there is one that's in the center that is entirely inside this, so we have 4. There are 4 calcium ions in each unit cell. Now, what should be the packing efficiency being certain to account for both ion types? All right, so the unit cell edge we have right here. There's a reason I gave these earlier questions, because they feed into doing this calculation. So 480 picometers, and we need to cube that to be the volume of the unit cell. It's going to equal that, okay, in cubic picometers. The volume of a calcium ion is going to be the formula for a sphere, 4/3 pi radius cubed. Calcium was, head back over here, calcium is 100 picometers cubed. The volume of an oxide ion is going to be 4/3 pi 140 picometers cubed. All right, the volume of all of the ions in the unit cell is going to be 4 of the calciums and 4 of the oxygens. Okay, so our packing efficiency is volume of the ions over the volume of the unit cell. So we have the packing efficiency is going to be this divided by this. So we plug it into a calculator. 4 times 4/3 times pi times 100 cubed plus 4 times 4/3 pi 140 cubed over 480 cubed. Okay, and again, in a normal calculator, you would just type in the numbers and do it. In this particular program, when I'm using it like a calculator, I have to tell it, in some cases, to turn it into a number, which is what I just did. And we get that it is 56.7% efficient. So packing efficiency to 2 decimal places is 0.057. All right. System 3, what do we do? So we need to identify all of the parts of this. This one you can just look up. This should be a gimme. Solid, right there. So A is 6, the solid. B is the liquid region, 7. C is the gaseous region, 9. D is, where's D? Is up here. That's the supercritical fluid, that's 4. E, that is the melting point or freezing point, so that's 1. F is this region, that is the evaporation condensation line. G, that is the sublimation line, 2. H, that is the triple point, 4. I, that is the critical point, 5. What are the possible physical states of CO2 on the surface of Venus? Select all that apply. So, Venus, let's come back over here. Venus has a temperature of 467 C and a pressure of 9 times 10 to the 6th pascals. So let's actually take this out. I'm going to move that over here so we can see that while we look at the at this chart that we just did. So our pressure, 9.3 times 10 to the 6th So that's going to be 9 megapascals. All right. So that's going to be right under this, okay, in that region. 467 degrees C. Well, Kelvin's even higher than that, so that's going to be off scale up here in that kind of range there. So that is clearly in the supercritical fluid region, and that's the only thing you can have. CO2 on the surface of Mars. So Mars has a range of temperatures and a range of pressures. So negative 140. So we can take 273 minus 140. I'm going to 273 minus 140 is 133. And the other temperature that we have is 30. So 30 plus 273. So 30 plus 273 is 303. So our temperature range is 133 to 303. All right. So we are looking from about 130, which is way down here, up to 303. So we're going across this range, okay, to right about here. Now, the pressures are 600 to 700 pascals. This is in megapascals. So we're way down below. So the only two states that we can have at this point are going to be the solid region and the gaseous region, because it's crossing the sublimation point. So our answers here are solid and gas. Okay, we now have the water phase diagram. Okay, this is the phase diagram for water. Does Mars allow for liquid water on its surface? All right, Mars on its surface. Again, we are going, this time it's in degrees C, so that's going to be more convenient. Negative 140 to 30, so negative 140 up to about 30. So it's going to be across this range in temperature. And atmospheric pressure, 600 to 700 pascals. So pascals here, so we're going to be pretty close here to the triple point, right? So the triple point we are told right here is 611 pascals. So in order for there to be liquid water on the surface, we have to be above that point and above this temperature. So it has to be above this pressure over and above the freezing point, which is that. So there, done. The next few questions, we use this data where needed. All right, we have a Mars rover. Okay, I'm going to have to expand this a little bit so we can see the side. We are doing heating curves from 140 degrees to 30 degrees. So again, on the same phase diagram, from about 140 up to 30. So we are crossing here, or we're crossing both of those. And we have 3 different pressures, exactly at the triple point, slightly below the triple point, and slightly above the triple point. At below the triple point, we are only going to have a single phase transition. We are going to have sublimation going on, and the temperature at which that is going to happen is going to be below the 273 degrees Kelvin, because you see how it moves it moves further to the left. So we are looking for a case where there is only a single phase transition, which is A through C, and we want one that is slightly below 0 degrees Kelvin, and that is going to be C. So slightly below the pressure is going to be C. Slightly above the pressure, we are going to have 2 phase transitions. We're going to have the melting followed by vaporization. They're not going to be separated by very much, and we notice that these 3 cases all have a very slight difference. So these 2 are different because where the first transition is happening at 0 degrees C, the other one is where it's happening below 0 degrees C and the second one is at 0 degrees C. So which one is closest to 0 degrees C? Well, it's the melting step, not the vaporization step. So this one is out. Now the question is going to be, does the melting take less energy than the vaporization, or does the melting take more energy than the vaporization? Well, if you look up here, the vaporization is at 45 kilojoules per mole, and the fusion, or what we use for melting, is the 6 kilojoules per mole. So D has to be the answer. So slightly above is D. Now, what happens exactly at this point? Well, if we look at the phase diagram right at that point, we're going to get there, something's going to happen, and then we're going to leave as vapor. Okay? So we're going to reach 0 degrees. So this one, and this one are the only possibilities. We've already done D. This one has another phase transition happening at a higher temperature. There is no second higher temperature phase transition happening. So the only possibility now is B. There we go. For the heating curve constructed at that temperature, calculate the heat added to 3 significant digits. Report your answer in kilojoules. Okay, so have 3 steps that are going on. We have heating the solid. We have converting to vapor. We'll talk about what that is in a moment. And we have heating the vapor. Okay. Heating the solid, we are going from minus 140 to 0. Heating the vapor, we are going from 0 to 30 degrees C. Okay. How do you heat something? The heat capacity times the temperature change. So we take the specific heat of the solid, which is 1.93 kilojoules per kilogram Kelvin. We multiply that by how much we have. We are told that we have a 100-gram sample of water, so we are multiplying this by 100 grams. I'm going to put that over 1 so that we can see what cancels and what doesn't. And we multiply by the temperature change. We are going up by 140 degrees, and a degree C in change is the same as a degree K in change. So we multiply by 140 K. So the kelvins cancel, but the grams and the kilograms don't. So we now need to do a conversion from 1,000 grams to 1 kilogram. Now the grams cancel and the kilograms cancel, and we are left with kilojoules. So our answer for this part of the step is 1.93 times 100 times 140 divided by 1,000. And that is 27.02 kilojoules in the first step. Converting to vapor. Well, we have a delta H for sublimation. We have a delta H for melting and then vaporization. But notice that even if we go through the liquid state, it's 6 plus 45 equals 51. We're going to end up with the same answer regardless of which way we do it. So we take our 51.0 kilojoules per mole of the water. We are multiplying by how much we have, which is 100 grams. And again, so that we can see what cancels, I'm going to put that over 1. Now we have to get from moles to grams. So 1 mole of water is, well, we go to our periodic table, 1.008 times 2, plus an oxygen, which is 15.999, 18.015. So 18.015 grams of water. So let's calculate that out. 51.0 times 100 divided by 18.015. Let's make sure everything canceled before we do that. Moles cancel, grams cancel, and we're left with kilojoules. Yep. So this step is a whopping 283.097 kilojoules. All right. Remove that. Heating the vapor. The last step is to take our vapor and heat it up. We take the specific heat of the vapor, 1.868 kilojoules per kilogram Kelvin, multiply by the amount that we have, 100 grams. Again, put it over 1 so we can see what we're canceling. And the temperature change, which is 30 Kelvin. Okay, the kelvins cancel. The grams and the kilograms don't cancel yet. So 1 kilogram is 1,000 grams. So our calculation is 1.868 times 100 times 30 divided by 1,000, and we get 5.064 kilojoules. We add these three together, 5.064, that's 3 steps, plus 283.097 plus 27.02, and we get 315.181 kilojoules. It's asking for kilojoules, 315.181. Okay. For the previous question, we had to make a choice between two different sequences of processes that occurred. The choice you made didn't impact the resulting calculation. What guarantees that? What was the choice we made? Well, we had to choose, as we hit this, are we going directly from solid to vapor using sublimation, or are we going from solid to liquid by melting and then liquid to vapor by evaporation? And it didn't matter because this sublimation delta H equals the fusion plus the vaporization delta H. What guarantees that that is going to happen? That is Hess's law, which says that enthalpy is a state function, so it doesn't matter which path you take from point A to point B, it will be the delta H will be the same. Okay. Which of the following are true about the physical processes of the water sample measured by the heating curves above? Select all that apply. So we can choose that the heating of single-phase steps as either endothermic, exothermic, or it doesn't have a change in energy. Well, we are putting heat into the system, which is raising the energy of it. That is endothermic. We are adding energy to it. The phase transitions are endothermic, energy neutral, or exothermic. Again, we have to add energy to it to make it happen, so that is endothermic. Now, do the phase transitions increase entropy, decrease entropy, or not change the entropy? Entropy is the amount of disorder. A vapor is much more disordered than the solid is. A liquid is intermediate, and so this is an increase in entropy. 39. We are now up to system 4. What intermolecular forces are present in the molecules of compound A? Okay, I need my other window up so that we can see what the molecules are. Okay, A, methane. This is a tetrahedron, and all of the bonds are equivalent, and they all cancel out. So this does not have a dipole moment. It also doesn't have ions. So the only thing this has is London dispersion. And it doesn't have hydrogen bonding because the hydrogens are attached to the carbons. There are no fluorine, oxygen, or nitrogen. But intermolecular forces are in compound B. Okay, one of the bonds is now different. That means this is going to have a dipole moment, especially given that fluorine is so freaking electronegative. So this is going to have dipole interactions. It's going to have dipole-induced dipole interactions and London dispersion forces. Compound E. E, all 4 bonds are the same this time. So that means they're all going to cancel out, and it is going to be nonpolar. So London dispersion is the only one you have. Compound F. Okay, this one probably requires taking a look at it because it's not just a tetrahedron. Okay, this is ethane. Takes a minute for that to come up. You know, that kind of looks pretty symmetric. So whatever's going on over here is going to happen over here. So this dipole, any bond you would have here has an equal and opposite bond over here. So this particular molecule is going to be nonpolar. So that means that it only has London dispersion forces. 43, compound K. We need to go back here to compound K. I'm in the wrong place again. K. All right, so we have a picture of it right here. Well, this one clearly is going to have a dipole moment because all 3 of these are kind of pointing down, whereas all 3 of those are kind of pointing up. So this one is going to have dipole-dipole, dipole-induced dipole, and London dispersion. Okay, boiling points comparing them. All right, compound A versus compound B. Compound A is methane. Compound B is this one, which has a dipole moment. So that means the most important thing is that the right compound, which is B, has a force type that the left compound does not, which is the dipole-dipole interactions. A versus E. A versus E. Both of those are nonpolar. The difference is that this has more electrons, so the London dispersion forces for E are going to be stronger. So the right compound has stronger London dispersion forces. A versus F. A versus F. Ethane is a larger molecule, and so you are going to have more London dispersion forces as a result of that. They're both nonpolar. So the right compound has stronger London dispersion forces. K versus O. K versus O. This one is the same thing, but all of them are fluorines. Now, this one has the higher boiling point, and that's because it has dipole-dipole interactions, whereas this does not. So the left compound has a force type that the right compound does not. K versus M. K, this one, versus M. Okay, both of those are polar, but notice that this one has one that's kind of in the up portion, whereas this one does not have one of the fluorines up there. So this one is going to be counteracting that one. This dipole moment is smaller than the dipole moment here. So K has a higher boiling point because it has because it is more polar. Both compounds are polar, but the left compound is more polar. 45. Surface chemistry of glass includes both oxygens and hydroxide groups as shown below. Okay. What intermolecular forces are present between the surface of glass and compound B, fluoromethane? Okay, let's see. There are no ions involved, so the first three are out. Dipole-dipole. These things are polar. Fluoromethane is polar, so we have dipole-dipole. If you have dipoles, then they can induce dipoles. You always have London dispersion. Now, here's the interesting one. This has a hydrogen that is attached to an oxygen, hydrogen, or fluorine. This has a fluorine with lone pairs. So you can have hydrogen bonding between these and compound B. So you get hydrogen bonding. All right. That question here sets up the answer for this question. In the image above, mercury on the left has a convex meniscus, though on the right, a concave meniscus. So let's stop and understand this for a minute. What's the difference? The difference here is that water can hydrogen bond to the surface. And so as a result of that, due to adhesive forces, it climbs up the walls. Mercury cannot do that, and so it is, while not really repelled by the walls, the attractions within the mercury are strong enough to pull it back together. So this is what happens when you don't have hydrogen bonding to the wall. This is what happens when you do have hydrogen bonding to the wall. So the question now is, of all of these molecules, because this has all of them, which of them have hydrogen bonding to the wall? Which have the concave, which is this one, like water? Well, anything that has a fluorine in it will be able to hydrogen bond to the walls. So it's easier to look at which ones don't. A and F don't, so therefore we need to mark everything except A and F. And we're done with 100%.